Welcome to the Deep Dive. This is where we sift through your sources, articles, notes, all sorts of things to really boil it down and get you well-informed fast. Today, we're diving into something that, well, it affects us profoundly, but often just flies under the radar. Space weather. It's kind of mind-blowing, isn't it? The sun gives us life, obviously, but it's also the source of these huge electrical, magnetic, thermal storms. And these storms mess with almost everything we rely on. Your phone, satellites, you name it.
That's exactly it. And it's not like weather here on Earth, rain or snow. Space weather is driven by this invisible flow, the solar wind. It's basically a constant stream of energy and plasma shooting out from the sun. And these invisible storms, they happen way up there, beyond 70 kilometers, and they can change really, really quickly.
Right. So our mission for this deep dive, then, we're going to dig into the sources you sent over. We want to get a handle on what space weather actually is, where does it originate, how does it interact with Earth's protective layers, and maybe most importantly for you listening, what are the real tangible effects on our modern lives? Because they're surprisingly big. We want to give you that shortcut, that distilled knowledge about this really turbulent but critical phenomenon. So let's get into it.
It's funny. I think a lot of us grew up picturing the sun as just this steady, calm ball of light. But the sources we looked at really drive home how much that view has changed, especially since the 90s, right? With satellites like SOHO. What did missions like that show us? Why isn't the sun this placid thing we thought it was?
Well, SOHO and others gave us this unprecedented view, revealing the sun is incredibly dynamic. It's constantly throwing energy out in multiple forms. First, there's electromagnetic radiation that covers a huge spectrum: gamma rays, UV, visible light, even radio waves. It's super energetic stuff, and it travels at the speed of light, so it gets here fastest. Okay, light speed. And then you mentioned the solar wind earlier. The sources describe it as this permanent flow of charged particles, electrons, and protons. And the speeds are just wild. Hundreds of kilometers per second normally, but during solar storms, over 2,000 kilometers per second.
Yeah, it's staggering. Imagine crossing the entire U.S. in, under 3 seconds. It's incredibly fast-moving plasma.
That's hard to even picture.
And then sometimes these particles get accelerated even more to near light speed. That's what we call cosmic radiation. These particles carry millions of electron volts of energy, enough to damage electronics or pose biological risks without shielding.
And you mentioned it's particles, not radiation like light waves. The name's a bit confusing.
Exactly. It's a historical term, cosmic radiation. But yeah, it's high-energy particles. Most come from distant stars, but the sun kicks them out too during big events.
Okay, so we had this constant stream, plus these super fast particles.
Yeah.
But it's not steady, is it? The sources talk about solar activity, these big bursts.
Right. The sun's output varies. There's this general pattern, the Schwag cycle, roughly 11 years, give or take, where activity ramps up and then quiets down. But the really dramatic space weather, the stuff that causes major effects, that's often driven by these sudden, massive explosions on the sun.
Explosions? Like what kind?
Well, you've got solar flares. These are intense bursts of radiation, especially X-rays. They're super fast. The energy reaches Earth in about 8 minutes.
8 minutes. Not much warning time there.
Not much at all. Then you have coronal mass ejections, CMEs. Think giant bubbles of plasma and magnetic fields erupting from the sun. They're slower than flares, but they carry enormous amounts of material and energy.
Okay, giant bubbles of plasma. Wow.
And there are also solar prominence events, another kind of eruption. All three are major drivers sending the stuff hurtling towards Earth.
Okay, so all this energy is heading our way. Thankfully, Earth isn't defenseless. We've got shields. Let's start with the atmosphere. The sources talk about the thermosphere, this upper layer from maybe 105 up to 600 kilometers, and it gets incredibly hot, 750 degrees Celsius. How?
Yeah, that heat is basically the sign of the atmosphere doing its job. It's absorbing the most dangerous solar radiation, the stuff beyond UV. If those high-energy photons got down lower, life probably wouldn't exist. The thermosphere stops them. It's our planet's first line of defense.
So it heats up because it's absorbing all that energy.
Exactly. And the air itself changes up there. Below about 200 kilometers, it's mostly molecules like we have down here, nitrogen and oxygen. But higher up, it's mainly individual atoms of oxygen. The intense radiation breaks the molecules apart. It's a whole different environment.
And within that, there's the ionosphere, too. How does that fit in?
Right, so that same energetic radiation doesn't just heat things up, it knocks electrons off the atoms and molecules, it ionizes them. So you get this layer, the ionosphere, which is a mix of charged particles, ions and electrons, and neutral gas. It's what we call a plasma.
The fourth state of matter.
Right, that's the one. And space weather is essentially all about the physics of this plasma. It's interesting. The electrons up there can be much hotter than the ions, like maybe 1100 Celsius for electrons, while the ions are only 800 C even during quiet times. Shows how they absorb energy differently.
Fascinating. Okay, so atmosphere is shield one, but then there's the big one, Earth's magnetic field, the magnetosphere. How does that work?
Think of Earth's magnetic field like a giant invisible bubble. It stands in the way of the solar wind, deflecting most of it around the planet. This creates a cavity, the magnetosphere. The outer edge of this cavity, where the solar wind pressure meets the magnetic field pressure, is the magnetopause.
Okay, the boundary.
Right. And normally, on the side facing the sun, it's about 10 Earth radii out, so quite far. But, and this is key during strong solar storms, the solar wind can push that boundary much closer, sometimes inside 6 Earth radii. That compresses our shield significantly.
Making us more vulnerable, I guess.
Definitely. The closer it gets, the more interaction there is.
The sources use this image of a drop of water for the magnetosphere's shape. Can you unpack that a bit?
It's a great analogy. The solar wind constantly pushes on the front, the day side squashing it, like a water drop hitting a surface. But on the back, the night side, the wind stretches the field lines out into this incredibly long tail, like the teardrop shape. It can stretch millions of kilometers.
Wow. And even with this shield, some solar wind particles sneak in.
They do, yeah. Especially into that long tail region. They can drift into the cavity.
And then they get trapped. Is that where the Van Allen belts come in?
Precisely. Closer to Earth, between about 5 and 10 Earth radii out, the magnetic field gets strong enough to trap these drifting electrons and ions. They get forced into creating this intense ring of electrical current flowing around the Earth. That's the Van Allen belt, or belts, really.
A ring of current.
Yeah. And eventually, through various processes like collisions, these trapped particles escape. They spiral down along the magnetic field lines towards the poles and plunge into the upper atmosphere. We call this precipitation. Just like rainfalls, these charged particles precipitate down from space.
And that's what causes the auroras, the northern and southern lights.
Exactly that. When these energetic particles, hundreds or thousands of electron volts, hit the atmospheric gases between, say, 70 and 700 kilometers up, they excite the atoms and molecules, heat them, ionize them, and when those atoms relax back to their normal state, they release that extra energy as light.
The light show.
The ultimate light show. And because the particles follow the magnetic field lines down towards the poles, that's where we see the auroras most strongly. There are actually permanent auroral ovals around the magnetic poles between about 65 and 75 degrees latitude because there's always some solar wind getting in.
Okay, so we have this incredible picture. The sun's power, Earth's shields, this amazing cosmic dance. But the big question for everyone listening is, how does this actually affect us down here, or our technology? Because the sources make it clear the impacts are real.
Oh, absolutely real.
Yeah.
And sometimes in surprising ways. Take ground infrastructure, for example. Space weather can induce these slow-changing electric currents in the ground itself, especially conductive ground. These currents can flow into power grids through grounding points and cause transformers and power plants to overheat, potentially causing blackouts. Big ones.
Wow. Induced currents from space messing with the power grid.
I like
That's
that.
subtle, but serious.
Very serious. It affects the 50 hertz systems in Europe, 60 hertz in the US, anywhere with long transmission lines.
And it's not just power lines, right? The sources mention pipelines, too.
Yeah, those same induced currents can flow between a long metal pipeline and the ground, increasing the electrical potential difference, and that accelerates corrosion. It's a hidden cost, weakening vital infrastructure over time.
Okay, so physical infrastructure is vulnerable. What about communications? We rely so much on radio waves, satellites.
Right. The electromagnetic disturbances from space weather affect pretty much all communication scales. Mobile phones, ground-to-satellite links, everything can be impacted.
What about specific things like radio blackouts? The sources mention those often.
Yes, solar flares are the main culprit there. That sudden blast of X-rays hits the ionosphere, disrupts it, and can cause immediate blackouts for high-frequency radio communication on the sunlit side of Earth. They happen quite often, actually. The sources say around 2,000 per 11-year solar cycle on average.
2,000. And the warning time is just 8 minutes?
Just 8 minutes. It's the travel time for light from the sun. So prediction is key, but reaction time is minimal for those.
Okay, and navigation. Things like GPS, which we all use constantly now.
Definitely affected. GPS, GLONASS, Galileo, all satellite navigation systems rely on signals passing through the ionosphere. When the ionosphere is disturbed by space weather, those signals get scrambled or delayed, leading to errors in positioning or even complete loss of signal. And another thing, solar radiation storms, often linked to flares and CMEs, can severely disrupt radio comms in the polar regions for days. That's critical for planes flying polar routes.
Right. Rerouting flights, communication blackouts. Okay, so satellites themselves, they're right out there in the thick of it. Orbital drag sounds like a big issue.
It really is. When space weather heats the upper atmosphere, the thermosphere expands outwards, becomes denser at satellite altitudes. This increased density creates more friction, more drag on satellites in low Earth orbit.
Like trying to swim through thicker water.
Exactly. It slows them down, changes their orbit, reduces their lifespan. Operators have to use precious fuel for corrective burns to boost them back up. It's costly.
And that expanding atmosphere must complicate tracking space debris, too.
Hugely. When the atmosphere puffs up during a storm, it carries all that junk, dead satellites, rocket parts with it, but in ways that are hard to predict immediately. So for hours after a big event, tracking debris becomes incredibly difficult. You lose track of potentially dangerous objects.
And the collision risk.
Well, the baseline risk for any one satellite might seem small, maybe 0.01%. But there are thousands of satellites and hundreds of thousands of trackable debris pieces. That risk adds up. It increases exponentially over time. And during these space weather events, when tracking is lost, the uncertainty and therefore the risk of a collision goes way up.
That sounds like a nightmare for satellite operators.
It is. And then there's direct damage to the satellites themselves.
Right, not just orbital mechanics. What
Right.
kind of damage?
Several kinds. The electrical currents flowing within the magnetosphere can degrade solar panels over time. They can also ionize coatings on sensitive instruments, affecting their performance. High-energy particles can penetrate satellites and corrupt the software in onboard computers. That can lead to malfunctions, loss of control, potentially total loss of the satellite.
Just scrambling the computer's brain, essentially.
Pretty much. And for satellites outside the main protection of the magnetosphere or during really intense storms, they face direct bombardment by high-energy protons from the solar, wind, or solar energetic particle events. The October 2003 Halloween storms were a prime example. The sources mentioned about 30 satellite outages linked to that event. 3 of those satellites were lost completely, permanently.
30 outages, 3 lost satellites. That must have been a massive wake-up call. What changed after that? How did the industry respond?
It really drove home the need for hardening satellite components against radiation, especially for missions going to higher orbits or beyond Earth. It also spurred huge investment in better space weather forecasting and real-time monitoring. The idea is to get warnings so operators can maybe power down sensitive instruments or put the satellite into a protective safe mode before the worst hits.
So shifting from just dealing with the aftermath to actively trying to mitigate the risk beforehand.
Exactly. It made the threat very real and very expensive.
Beyond the tech, what about biological impacts? Astronauts, air crews?
Yeah, there's a recognized risk. Increased radiation exposure during solar events, especially those solar radiation storms, can potentially lead to DNA changes. It's a major constraint for planning long-duration spaceflights, like going to Mars. Shielding is crucial. Even for airline crews on high-latitude flights, there's monitoring of radiation doses.
And down here, what about the climate change connection? Some people seem to link solar activity to global warming.
That comes up a lot. But the scientific consensus, based on, mountains of data, is pretty clear. While solar variations do affect Earth's energy input slightly and can have some minor regional climate effects, the changes are just far too small to explain the significant global warming trend we've seen over the last century or so.
So a minor player in climate, not the main driver.
Not the main driver of the current warming. No, that's overwhelmingly linked to human activity.
Got it. Okay, let's talk money. Power grids down, satellites lost, corrosion. The economic impact must be huge.
Absolutely enormous. Studies in the US and Europe have tried to put numbers on it, and they run into the billions of euros or dollars. Think about the industries affected. Insurance paying out for satellite failures, banking systems potentially disrupted, power companies facing repair costs, airlines rerouting, even tourism.
Tourism, how?
Well, Aurora tourism is a thing, but also the emerging space tourism sector is highly sensitive to space weather conditions. So yeah, the financial stake in understanding and predicting this stuff is massive.
It really is incredible that space weather as its own field is, well, relatively new, just the last few decades, really.
It is, yeah. But it's become absolutely critical, hasn't it, given everything we rely on that it affects.
For sure. And prediction is key.
Vitally important. Being able to forecast these events allows us to take action. Adjusting power grid loads, maybe holding off on sensitive satellite operations, warning astronauts.
And those warning times are crucial, but they vary a lot, don't they? You said 8 minutes for flares? That's barely time to react.
It's incredibly short for flares impacting radio, yes. You basically get the alert as it's happening. Solar radiation storms, maybe 10 minutes to a few hours warning, which is slightly better but still tight.
But the big geomagnetic storms, the ones from CMEs.
Ah, that's where we have a bit more breathing room. Because CMEs travel slower than light, maybe taking 1 to 4 days to reach Earth. We can often see them leaving the sun with coronagraphs on satellites. That gives us potentially several days of warning before the main impact hits the magnetosphere.
Several days. Okay, that makes a huge difference. Time to actually prepare.
A massive difference. That's enough time for power companies to adjust operations, for satellite operators to safeguard assets, for airlines to change flight plans. It's why improving those CME forecasts is such a huge focus. So yes, the discipline might be young, but its future is incredibly important because of these global impacts and the economic stakes.
So wrapping this up for you, our listener,
Mm-hmm.
it's pretty clear how tied we are to the sun, isn't it? Even its moody side. From these invisible winds causing technological chaos to the sheer beauty of the aurora, space weather is this constant, powerful force. We're really just scratching the surface of fully understanding and predicting it, but it's obvious we need to protect how we live now.
It certainly gives you a new respect for that quiet-looking star and how much our technology exists almost at its mercy.
Definitely. And here's something to think about as we finish. As we become even more reliant on space for communication, navigation, watching our own planet, how much more effort will we need to put into understanding and mitigating space weather? Could it force us to build satellites differently, like tiny armored tanks? Or could it even change how we design things down here on Earth, our power grids, our pipelines, in ways we haven't even thought of yet? Something to mull over.